Okay, let's kick off. Welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh, and we'll talk about the purpose in a minute. But if you're new to us, you can find out all about what we do on our website, and there you'll find links to our Facebook page, our Twitter page, and most importantly these days, our YouTube channel, where all our lockdown talks and the previous parts of this introduction to astro-imaging can be found. So please take full advantage of that. Next one then, please, Matt. And coming up on Friday the 31st, we'll have a review of the sky in August, and then a bit of a round-robin catch-up of what we've been doing during the period we've been failing to meet physically, but had a fairly intensive campaign online. We're not meeting in August other than the imaging group, which is a members-only group, which will meet on the 12th of August. And on Friday the 4th of September, when we're due back, we have Professor Duncan Lorimer going to talk to us about fast radio bursts. So that should be really interesting.
And just a reminder, the imaging group is for all ASE members, not just imaging group members.
Sorry, yes, it's you're quite right, Mark. It's all ASE members. So obviously, if you're a guest looking on YouTube, you can join us. Look on our website, and you'll find the joining instructions, and it's a terrific value for money, especially with the content we've been giving out in the last 6 months. I'd also like just to take this opportunity to welcome 3 new members. I mentioned Emma Burrell last meeting, but again, can I ask you to welcome Emma Burrell, Sarah Bullman, and Douglas Henderson, 3 new members we have. And you unmute and welcome them in the normal way. Right, well, I hope if you're watching, I hope you enjoy tonight's session. Next slide, please, Matt. So we're going to be talking about astro-imaging. We've had 4 elements to it already. As I said before, they're available on YouTube, and they'll make much more sense to watch those if you're a beginner than jumping at this end. We had a fantastic talk on Wednesday night from John Hopkins and the Applied Physics Laboratory on the Parker probe, and all that resource and energy that came out into that talk, using all the resources available, set the bar fairly high. So it's over to you then, Mark.
Thank you for that, Andrew. Well, this is part 5 of a 4-part course, really. So this was a bit of an afterthought, based on the fact that we've had 2 talks about citizen science and how we can get involved. So intro to astroimaging part 5, or is it time to move on to the next level, astronomically speaking, or is it time to grow up even, astronomically speaking? Is that a bit rude? I don't know. So anyway, you can now create amazing images. You've all been watching parts 1 to 4, and you've all been practicing, and you can create superb images. You can enhance your data, push it to the limit, pull out the finest of details. But is that going to be enough for you? I mean, that was where I started, I suppose, and for a long time I've been doing pretty pictures, but after a while you realize maybe you want a little bit more. So as well as doing all that, you can add to the sound knowledge of the universe, our universe, using your own kit in your own garden, using the skills you've already developed for imaging, and who knows what you might actually discover. So I think a lot of us in this society, with the kit we've got, can actually do quite a bit more and get involved. So let's do some science. Andrew. So this is an intro to these projects, so you will need to investigate each one more fully. I'm not going to give you the finest details on each one, obviously, because it would be too much to actually do. But I'll introduce you to some of these things, and then if they interest you, you can take them a little bit further, and we'll discuss these at imaging groups and things like that. So the sorts of things you can get involved with using your imaging techniques are variable star monitoring, looking at the magnitudes of comets, supernovae, novae, and two specific projects that we know about, the HOYS project and the Exoclock project we had talked about earlier on in this session. So you know a little bit more about those, and I'll talk about those specifically. Wrong one. So these are the sorts of things we're talking about here. So really what we're talking about is photometry. So everything here is photometry. It's about measuring brightness of objects, from the Greek photo and metry, measuring the flux coming from an astronomical object. And CCD and CMOS cameras that we use now are particularly good at it, certainly better than the human eye, but up to a point. So for your camera and sensor, you'll have a graph something like that, that the response is pretty linear for most of its curve, but after a certain point, it stops being linear. So if you try and measure things in that non-linear area, you'll start to get some strange effects. So you need to know which bits of the sensor response for your camera is linear. And it's usually up to about 2/3 of the response of it. So if you've got a 16-bit camera and it can take 65,000 bits, 65,000 photons in its register effectively, then maybe up to about 40,000 is the linear part. So photometry, well, let's take an image of some stars like that, and you have some photometry really. That's an unprocessed raw image. It's not particularly interesting, but it's got something in there. We discussed calibration in previous meetings about calibrating the data with your bias frames, your darks, and your flats. Once you've done that, you have the potential to do some science. And with that image there, maybe even work out the distance scale of the universe, believe it or not. I'll come on to that in a minute. I did promise on the Astro-imaging, the imaging group WhatsApp, that I would tell you how to ruin your data. Will's particularly interested in knowing how to do a deep destroy. Basically, turn it into a pretty picture. So everything you've learned already, that will destroy your data. Stretch it, normalize it, apply curves, adjust the color, put makeup on the pig, all that sort of stuff. You know, that's how you will destroy your data. After you've done that, there's not a lot you can find in there. So I've been working on the HOYS project for about a year and a half, and these are all the images I took of the Pelican Nebula over about 18 months, stacked, stretched, and processed to make a pretty picture. It's actually almost worthless scientifically, but it looks quite nice. I say it's almost worthless, but you can actually dig out some interesting objects. So, for example, that star there, V1490 Cygni, you say, wouldn't you? Not sure. Alan's saying something. There's some interesting stuff in there. So those 18 months of images of that star will give us some nice light curves and some color information. There's also quite a lot of other interesting things in there as well. You can see some Herbig-Haro objects. So the image looks nice, but once it's processed like that, it's not anything like so useful. But you can do both. So you can use your data and you can create pretty pictures out of it afterwards. So a bit about magnitudes. Alan's covered some of this in the navigating the night sky thing. I'll put an equation in there and then not talk too much about it. But basically, it's a logarithmic scale. So the magnitude, the brightness of a star that we see is a logarithmic scale. The flux coming from the star over a standard flux level, 0 level, and that's the brightness scale. What that actually means in practice, the sun, the brightest thing in our sky, is about -26, the full moon about -12, Venus -4, Sirius, the brightest star, -1, and the blue star Vega overhead in summer, that's around about magnitude 0, just below that. Polaris, pole star is 2, and naked eye visibility is around about 5 to 6. And Pluto is 14. So that's how we use the magnitude scale. Those are apparent magnitudes. So those are the magnitudes that we see how it appears to us on Earth here. There's something called absolute magnitude. That is how bright the object would appear if you place it 10 parsecs from Earth. So about 32 light years. If you put all the objects in the universe that 10 parsecs from Earth and look at the brightnesses, that's called absolute magnitude there. And that's the intrinsic brightness. So that's a brightness associated with the star itself, how large, how bright it actually is, rather than just how it looks to Earth. I say that there because we might discuss something about that shortly. What that means is if we know the capital M, the absolute magnitude, and we know the apparent magnitude, how bright it looks to us on Earth, then we can work out how far away that object is, or substituting other values in there. So it can be useful. Magnitude is also different with different filters, so in different colors, different wavelengths of light. There's a standard set of filters that you tend to use for photometry called the Johnson-Cousins set of filters. UBVRI, U, ultraviolet, B, blue, V, visual or green, red, and infrared. And you can actually learn a lot about the objects from imaging them in different filters. For example, an object might get redder, and that might indicate there's some dust going in front of a star, for example. I remember studying this at university and carrying huge piles of astrophysical journals back from the library just to find one line in each one about photometric systems, but I've forgotten everything I knew about it. Supernovae. Let's start with supernovae. The picture we had earlier on, pretty dull. We stretch it slightly, and in there is actually a supernova in galaxy NGC 3643. Stretch it a bit further, and that black dot there is a type 1a supernova that outshines the whole rest of that galaxy. So that one star went supernova, and it's outshining the however many billions of stars in that galaxy, which just goes to show what a cataclysmic event a supernova actually is. Type 1As are very useful for measuring the distance scale of the universe. I mentioned that earlier on. They're what's called one of the standard candles because they all have very similar absolute magnitudes. So how do you measure their brightness? There's a light curve of a type 1A supernova, a steep rise, steep fall, and then a slower tail off. How do you measure the brightness in the sky? Well, there's various free bits of software you can use for photometry. Munipac, MuniWin is the Windows version of that. Astro-imaging, an aperture photometry tool, another APT, not to be confused with astrophotography tool. And I'll show a little bit how we can use these. So this is MuniWin. It's quite a simple piece of software. It's free. It will calibrate your files for you with your bias, flats, and darks that you provide. It'll run photometry for you fairly automatically. It'll identify all the objects in your frame, measure the flux coming from it, and calculate the magnitude. Now, those magnitudes are not apparent magnitudes, those are instrumental magnitudes, you call them. So those are different for every telescope, camera, filter combination, and all sorts of other factors as well. So that is a magnitude for you with your bit of kit. This is something called the Object Inspector within MuniWin. So it's identified all the objects, put circles around them. And if you click on one, on the right-hand side here, it's given it an instrumental magnitude of 12.39 with an error of 0.0031. So nice and straightforward to use. That value there is not a value that we can use elsewhere at the moment. That needs to be calibrated. So how do you calibrate magnitudes? Well, we were looking at a star that varies in brightness there, but there are a lot of stars in that image that don't vary in brightness, fixed stars. We can look up in something called Simbad, a massive online astronomical database, and that's a very useful website to get your head around if you have the inclination. We can look at these fixed stars, check for the magnitudes in the same filter, and that will help us to set the 0 point of the image. So how many counts in your CCD count for 0 magnitude, and then we can calibrate our instrumental magnitude using that 0 point. That's a bit of a simplification, but it's fundamentally the way it works. If we were to use Astro-image for us for this operation, it will solve the image for us. So if we click on the actual star itself, it will take us to Simbad, and Simbad shows information such as this. So a small view of the star, and lots of information about its coordinates, its brightness, magnitudes and different filters, parallaxes, how far away it is, proper motions, etc. A lot of information you never knew you needed, but you probably will need some of it at some point. So that's calculating a single magnitude of an object. The same technique applies if you want to create some light curves. So a variable star, for example, over a long period such as that star there. Both these bits of software will you take a stack of images instead of just a single image, calibrate it, process it for you, correct for things such as air mass, the altitude of the object in the sky, and it will create a very nice light curve. So if you want to go into this in more detail, then I suspect you'd probably want to join the BAA variable star section. There's a lot of information there, and get more involved. Or the AAVSO, that's the American Association of Variable Star Observers, one of the probably the biggest organization for variable star observing for amateurs. Let's move on to comets, since that's quite topical at the moment. This isn't too easy. What do you measure? A comet's made up of a nucleus, a coma, a tail. If you look at some of these pictures, these are images of comets I've taken over the last few years. They're all very different. The one bottom left is the one that's around at the moment. How do you measure that magnitude? Well, I actually subtracted the stars out of that anyway, because they were trailing and multicolor anyway. The other images, not so easy. So what do you actually measure with a comet? I think the current thinking is that you measure the whole brightness, so of the whole comet, the tail as well as the coma. So within that circle there, we need to measure the sky background, the comet, and we also need to subtract the stars as well. So we're subtracting the sky background and the stars from the comet that's in there, and that will leave us with the magnitude of the comet. And then we need to find the image 0 point as before to calibrate it. It's not very simple. Again, I think during the BAA comet section for that would be a good idea. There's information on that website as well. And there is a piece of software that people like to use for comet magnitudes called Astrometrica. It's not free, but it's not overly expensive. So citizen science, moving on from just doing stuff ourselves, we're all familiar with Zooniverse. We've had talks about this. So we know how we can hunt planets, we can classify galaxies online, we can count penguins, as Peter's doing on his screen at the moment, and we can pair meerkat. No, that's not right. It's not part of citizen science. And we've had 2 talks about citizen science with a telescope recently. So a lot of citizen science on Zooniverse is about doing stuff with other people's data online. This is about capturing the data yourself with your telescope, processing it, uploading the data, and getting to be a co-author on published papers. So we had the Hoy's talk and the Exoclock talk. So I'll talk a bit more about those now. Hoy's hunting out bursting young stars. The way this works is amateurs take the images of these interesting areas, the things that we're imaging anyway, such as the Orion Nebula, Cocoon, Rosette, Elephant Trunk, lots of other interesting ones as well that we would normally choose to image. They need amateurs to do it because it's very hard to get time on larger telescopes to do long-term monitoring. As we discovered, I think the LSST or Vera Rubin telescope is going to be doing more of that in the future. It's going to be monitoring the whole the northern hemisphere, is it, in every couple of days in lots of filters. So that may get better. But the aim of the HOIS project is to have amateurs image all of their objects. There are 17 plus a number of alerts in every filter that they can every day, and that's spread around the world with a number of amateurs and university observatories. And the idea is to prevent loss of data due to bad weather or unavailability of telescopes. So what does taking part in HOIS actually mean? What does it look like? It is a relatively simple project. You take images of one or more of these objects, and as often as you can or like to do that, using whatever telescope you have, 2 inches, 40 inches, whatever. The smaller telescopes are actually quite important for the brightest stars, because if you take long exposures using larger telescopes, those stars saturate very, very quickly, and all that data is lost. So 2-3 inch telescopes are great for monitoring objects such as the Orion Nebula, where there are some interesting objects. You can use whatever camera you've got, be it mono or color, including a DSLR, and in any filter. And the only restriction is they don't accept images from clear filters. And if you think about a color camera, it's actually a mono sensor with 3 color filters in front of it anyway. So you have data from 3 filters within your color image. And I'll talk about that in a minute. So you calibrate your data as before with bias darks and flats. You upload your data to the database server and you process it online. I'll show you what that means. So for me in the summer, I tend to monitor things like the Pelican, the Elephant Trunk, and the Cocoon Nebula. I would take 3 3-minute exposures for each filter, red, green, and blue, and sometimes hydrogen alpha. Calibrate each file, stack 3 frames for each object and filter, and that gets the data down to about magnitude 18. And you can get accuracies between 0.02 and 0.1. The fainter the object you're measuring, the larger the error seems to be, as you'd expect. Upload up to the server and then process it online. And the online processing is really converting from instrumental magnitude, as we discussed, to a calibrated magnitude. So this is what that calibration looks like for HOIS. The top graph, the black dots are the instrumental magnitudes spread around this central axis here. You can see it goes up to about magnitude 18 there. The bottom graph is after the calibration's been done. The red dots are now these calibrated magnitudes, and it's actually taken the data out to about magnitude 19. It looks quite complicated, but it's actually quite a simple process. Basically, it's about selecting the range of objects that aren't saturated and that aren't too faint to get useful information out of. So the process takes just a minute for each image. So these are the last 2 sets of images I took for the HOIS project. IC 5070, which is the Pelican Nebula, pretty dull and boring there, and 1396A, that's the Elephant Trunk Nebula. But what you can do after you've done the science on your data is stack it and create pretty pictures. So, excuse me. So this is all my Rosette Nebula data taken in the summer in hydrogen alpha, in the winter, in hydrogen alpha, stacked and turned into a mosaic. And that's quite a satisfying thing to do. The data is destroyed now, it's not usable, but the original raw images are still very useful. And this we saw earlier on is the Pelican Nebula. And in that, by stretching it and stacking it, you can dig around and find lots of information. Interesting objects such as these Herbig-Haro objects there, which are also associated with young star formation, extreme stellar winds, I think. And in the few years that the HOIS has been running, amateurs and universities have uploaded 29,000 images to the server. And from that, the software has managed to extract 133 million magnitude measurements in those images. And that's very useful information. A note about color cameras. We've used Cyril in the previous part of the course, and you can calibrate your data in Cyril as before with your flats, darks, and biases, and you stack them to go deeper, to go fainter. And then what you need to do is to extract the 3 individual color FITS files from that. So here's an image within Cyril. It's a globular cluster, so it's not a young star cluster at all, for example. And you can see it actually already has extracted the 3 channels at the top. And then there's an option at the bottom in one of the menus to actually extract the 3 filters there. And that is the data done for you. So you can get 3 filters worth of data from one image with color cameras. It's not quite as accurate as doing a mono camera with a single color filter, but it's not bad, and it's certainly good enough accuracy-wise for the HOIS project. So color cameras are a good way to go for HOIS. A bit about the science for HOIS. Looking at the light curves from the data that we've extracted from these images. This is from an object in the Elephant Trunk Nebula. I've been monitoring it a lot over the last year or so. You can see these are 3 filters. The infrared is the black one, red is red, and green is V filter, the green filter. About a year and a bit ago, it had a nice outburst. Not exactly sure why yet, and calmed back down to previous levels. And then just about a month and a half ago, it started another outburst, but it has now peaked. It rose at a different steepness and peaked at a lower brightness, and is now going down. So this is fairly recent data. So that the analysis job now is to work out what's going on in this star forming region. What's this star actually doing? And the sorts of things that are going on in there maybe are star spots, material falling onto the star, material going in front of the star or moving out away from the star. Here are some other plots for other objects as well. There's a lot going on in these things, in these young star forming regions. Could be protoplanets forming and going in front of the stars as well. So if you remember from our HOIS talk, these are one of the pictures that Dirk showed us about how planetary systems form with the protoplanetary disk and planetary debris fields and so on. And a nice picture of what might be going on in there, an artist's impression. So there might be material blocking off the light or revealing the light from the star. So your simple images are actually contributing to working out what's going on and how these stars are actually being born. One last slide on HOIS. Fairly recently, they've got a partnership with the Las Cumbres Observatory. So if you haven't got access to equipment and you want to get involved in HOIS, then you can get to use these LCO, the network of 0.4 meter telescopes around the world in places like Hawaii, Texas, Canaries, and you can get to use those scheduled images to be taken, process the images on the server and have a look at the light curves, and you can even make pretty pictures out of the images if you want to, and you can really get involved in the science afterwards as well. So if you want to get involved in this, full training will be given, some videos on the website, some of which I created, and we have 3 members from the society already involved in this, and they've already taken images, Will and Nigel and Neil. So if you want to have a go at that, go to the HOIS website and apply there to take part in that project. It's quite good fun, I think. You can ask Neil and Will's views on it at the end of this, maybe. Okay, exoclock. We had a talk from Anastasia and Angelos a few months ago. This is to help out a space mission called Ariel, and its purpose will be to take spectra of planetary atmospheres. And it's going up in 2028 for about 4 years. There's only a very short period when you can get those spectra, and that's when the atmosphere of the planet goes in front of the limb of the star. And that's a very short period of time, so you need very accurate ephemerides for that. So the idea of the exoclock project is to monitor these transiting exoplanets, make sure you know exactly when the transits are going to start and end, because a lot of the exoplanets they're going to be looking at haven't been observed since discovery, or not very often, and some of the transit times are actually incorrect. And they need amateurs to record these transits again. There's a simple schematic of how it works. So planet pass in front of the star, drop in the light coming from the star, and then it increases again as the planet passes the atmosphere. You need a reasonable telescope because the magnitude of these stars are 10, 11, 12, 13, so not the faintest, but not the brightest. And also the drops in brightness are no more than about 0.02 of a magnitude, so that's quite a small drop that you're trying to measure. They initially wanted only mono CCDs, but they're finding out that CMOS cameras are also now very useful. They prefer us to use red filters because that reduces the effect of limb darkening on the light curves. But clear filters are also fine for this project. Color cameras, you can now extract the red frame as we saw already. You take images that are something of the region of 30 seconds to 3 minutes, depending on the magnitude of the star. And you need to monitor the star an hour before and after the transit is due to allow for any variation in that transit time and to help with calibration as well. What that can mean is anything from 3 to 7 hours of imaging, which is a bit of a problem, really, if you live in Scotland, because we don't have that amount of clarity at night if you need it very often. Use a piece of software called HOPS, which was specifically written for the project. And that's really a nice piece of software to use and very easy, and comes up with a nice picture at the end as well. And the project will also schedule objects for you to look at that's suitable for your location and your equipment, although it doesn't take the Scottish weather into account. So here's an example of WASP 104b that I monitored earlier on in the year. It's magnitude 11.3 in the red filter, and that required 50-second exposures. You have to take various exposure lengths to test it out to make sure that you don't saturate the star, that you keep all the information you can, and that you're using the linear part of your sensor as well. And unfortunately, there are no pretty pictures here. A few dots of white light, and that's the star we're looking at. We don't obviously see the planet itself. My telescope's certainly not big enough for that. And then using the software, so we've taken however many hours of images, 50-second images, maybe 4 hours of images, so that's quite a lot of images. We drop them into the HOPS software here. We specify bias, dark and flat files, specify the header terms that we're going to use, the exposure time and the observation date. And then the software will automatically calibrate the data, and it will align all your images so that the star that we're looking at is in the same place on every one. The next stage is to run the photometry. To do that, we need to choose a number of comparison stars, anything up to 10 comparison stars, but at least one, preferably 2 or more. And we need to choose comparison stars that are close to the target star, the red one there. They're not variable. I've chosen variable stars before, which wasn't a very useful thing to do, because if it was varying and the star was varying in brightness from the exoplanet transit, you didn't know which one was which, but that was just a mistake. You need to find a star that's a similar spectral type. So it's going to be going to work the same in the filter that you're using, and also of similar brightness. The HOPS software will allow you to check SIMBAD automatically. Once you've selected your star, it will take you to SIMBAD, and you can check whether it's variable, what the spectral type is, and brightness, and so on. And then run the photometry. So that goes through, checks the target star, and measures its flux and compares it to the flux of the comparison stars. That should take away all the changes in atmosphere, transparency, and so on throughout the night. And then what you're left with should be the actual transit of the star, of the planet in front of the star itself. And here's the initial fit done to, this is the Qatar 1b exoplanet for this image. It attempts to fit the data to an exoplanet transit curve. Because we know it is an exoplanet transit, we know there's a sort of curve template, and you try and fit the data to that. And you can see that's a fairly good fit for that data. you will find the data is fairly scattered, but because we know it's going to fit that template, we can fit the data to it quite well. But for a final fit, we need to upload it to the server, and that gets fitted online. So here's my information, my monitoring of WASP-4 and 4b, and from that data, it calculated that the observing mid-time was actually 13.8 minutes earlier than the predicted one, the one that they had in the ephemeris already. That's one observation, but in collaboration with Mauro, I think he was doing his in Portugal, I'm not sure, I can't remember. He also did it at a similar time, and his calculation showed that it was about 17 minutes earlier. And with other information, we have worked out that it is about 15 minutes wrong. So that's exactly what exoclock is for. So in collaboration with other people monitoring these exoplanet transits, we can correct the ephemeris for that exoplanet transit. And that is now published, or almost published, in the paper. And because I supplied some of the data, I'm a co-author on that paper as well. So exoclock is a bit tricky to do. It certainly takes a larger amount of time to do, but it is very doable for amateurs. The Scottish weather is the challenge. There are very few nights where you can get 5 to 7 hours of observing time. But if you think about it, you are observing exoplanets with your own kit, and it's only what, about 25 years since we discovered the first exoplanet. So I think that's pretty cool. So that's just a brief overview of the sort of imaging for projects you can do. John's saying you can actually do occultations of stars by asteroids as well. That's very, very true. And lots of other things as well. So imaging group people, you can take amazing pictures and you can do some science at the same time. So next time, well, I've run out of tosh to talk about. I've made up enough stuff now, I think. So I think if you want to know any more about imaging, then join the imaging group. That's where we'll discuss many of these things, as well as learning how to use a Yelexop, which you'll never have heard of if you're on the WhatsApp imaging group.
Mark, that's brilliant. Thank you very much. Can we show our appreciation? And I know just how much effort you put into all these, but I would like to give a warning. For anybody new to astronomy who's looking at this, do not be put off. Look at the earlier parts of the imaging course. We start at the very basics. If you just want to look at the stars, that's fine. If you want to take some pictures or images, that's fine. This is for, I think, when you've become fully confident in using the kit and you want to stretch yourself that bit further. So do not be put off by the technology and the techniques involved here. But it's great fun if this is what you want to do and you can make a real contribution to science. Having said that, we'll take any questions.
Feel free to pick holes in my theory as well, because it's a bit dodgy in places.
Did any questions pop up, Peter?
Not really, no, apart from just to confirm that our meeting in September will be a Zoom meeting.
Correct.
No.
And John's saying a good way to destroy your data is to save the image as a JPEG from your DSLR in processing. That will definitely be the case as well. Save your data as raw as you can. And a lot of these projects will use FITS files as well. Sean, you have a question?
Yeah, thanks, Mark. That was really informative and entertaining as ever. It was really just a general question about time. How do you find, I suppose it depends on people's, life circumstances and their work, etc. But in terms of how much time you have to devote to what you're doing, do you find that being involved in some of the citizen science projects takes a fairly dedicated chunk of time every single day, or is it something you can balance over a longer period?
The HOIS one is actually not too onerous in terms of observing time. If you're setting up to photograph something anyway, to image something anyway, then 10 minutes at the start or at the end of your session will actually do something. You know, after that, you need to process the data, but that can be done in 10-15 minutes for your night's observing session. But yeah, it is obviously time, and you've got to decide whether you want to do that or not. If you're imaging the object anyway, then the chances are you'll be able to use the same data files that you're taking to make a nice picture out of. So yeah, X o'clock, it kills me actually, because you need 5 hours of data. It's quite often 3 o'clock in the morning by the time I'm having to close up the dome, and by that time I've had enough. But it's very satisfying that when you finally do get your first exoplanet transit, if you think about what's actually happening there, it's quite amazing that amateurs can do that now. So yeah, it is a challenge time wise, but working in the daytime, you've got night. You don't need to. Astronomers don't get up before midday, do they?
Thanks.
Any more?